Why waste time in commute and spend a lot of money for NEET UG coaching? Parents, do you want your kids to achieve top scores in NEET? India's leading online NEET coaching, 100% success. NEET UG. TeenEinstein.com. At TeenEinstein, we focus on NEET coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany and zoology with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry and biology for rigorous practice, concept understanding, evaluation, quizzes and thousands of videos. Limited offer, 40,000 per year. Book your class. TeenEinstein.com. Contact 99402 49720.
Hello everyone, welcome to this video. In this video, we are going to talk about moving charges and magnetism. So in the previous lectures, we have talked about electrostatics where the charges were at rest and they produced fields and forces, and we studied what happens when the charges at rest are producing forces. And now, and then after that, we talked about when the charges start moving, they give rise to a current. So we talked about the conductors, insulators, and when there is current inside an insulator or a conductor, then it gives rise to resistivity, resistance, and we talked about all these things. Now, in the next step, we are going to see when a charge is moving, it does not only produce electric field, but it also gives rise to magnetic field. So that's why moving charges produce a magnetism also. So in this chapter, we are going to see this topic in detail. So in this, we are going to talk about magnetic force first, then motion in a magnetic field, that is motion of a charged particle in a magnetic field, motion in combined electric and magnetic fields, then magnetic field due to a current element, Biot-Savart law. This is similar to the Coulomb's law and Gauss's law, which we studied in the case of electrostatics. Then finally, we will talk about magnetic field on the axis of a circular current loop. Okay. First, for about 2000 years, we knew about electricity and magnetism separately, but we did not know that they were connected. So in 1820, Hans Christian Ørsted noticed that a current in a straight wire caused a noticeable deflection in a nearby magnetic compass needle. He found out that the alignment of the needle is tangential to an imaginary circle which has the straight wire as its center and has its plane perpendicular to the wire. So there is a similar setup shown here. So if there is a current carrying wire that is going through the center like this, and this is the plane of a paper, and you keep a magnetic compass needle here, whenever there is a current passing through this wire, then the magnetic compass needle showed a deflection. Then only he realized that there is a connection between the current, that is the electric charge is moving, and the magnetism because of the deflection of the compass needles. Now, he also noticed that reversing the direction of the current reverses the orientation of the needle. For example, in this picture, if you see, the current is coming out of the plane of the paper and the needle is showing in this direction, it aligns itself in a circle around the current carrying wire. But if the current direction is reversed, that means the current goes into the plane in this case, then the magnetic compass needle still forms a circular shape around the needle, but it reverses its direction. Now the blues are aligned in the right hand side. So this is also something he noticed, and from this it was concluded that moving charges or currents produced a magnetic field in the surrounding space, because if they produced a magnetic field only, then there will be a deflection in the magnetic compass needles. So it is concluded that the current is the one that is producing the magnetic field which affects the compass needles. And this is another illustration of a current carrying wire going through a plane of paper. These concentric circles can be interpreted as ion fillings. If you have a current carrying wire on a piece of paper that is going into the plane or coming out of the plane, you just put ion fillings around it and they will align in this way as concentric circles, indicating the magnetic field lines that are produced because of the current carrying wire. Okay, so we will talk about magnetic force and what are the sources of magnetic force and what is magnetic field. So before going into that, we will revisit our what we studied in the case of electrostatics. So we know that electric field interaction, the charges are interacting within each other because of the electric field. So interaction between two charges happen like this. There is an electric charge Q which produces an electric field E, which in turn exerts a force on another charge. So for example, if there are two charges, this is how they interact. First charge produces an electric field and that electric field is exerting a force on the other charge. And we talked about this electric field E, which is given by Q by 4 pi epsilon 0 into R square, and the direction will be away from the field, away from the charge if it is positive and towards the charge if it is negative. So this is given by Coulomb's law and even Gauss's law, and this is the electric field produced by a charge. And we know that the force exerted by this electric field on another charge is given by Q multiplied by this field. So small q capital Q R cap divided by 4 pi epsilon 0 R squared sums up what happens when two charges are interacting. Now let's see the case of a magnetic field. So these static charges produce an electric field. In this first case, both the charges are at rest. So they are static charges and they produce electric field. What if these charges start moving? Then they give rise to current. So the currents or moving charges produce a magnetic field in addition to the electric field. So the magnetic field they produce is given by B of R. So why we say B of R? Because it is defined at every point in space. It's a function of R. R is nothing but the position vector from the origin. So B is the magnetic field produced by a moving charge. And it's a vector field and is defined in all points in space. That's why we have B of R. It is found to obey the superposition principle. So what do we mean when we say it obeys the superposition principle? If you have 2 or 3 sources of magnetic field, you can take one by one and add them vectorically. Then you can say that this is the sum of the magnetic fields that are present in this particular point. So this is what we mean by superposition principle. So this is about how magnetic field is produced by moving charges. Okay. Now magnetic field and Lorentz force. Now we know what is magnetic field and we know how it is produced. Now let's say if you bring a charge Q which is moving with velocity V in the presence of an electric field and the magnetic field, what happens? So this is easy to answer in terms of electric field because when you bring a charge into the electric field, it exerts a force of Q multiplied by E. But the case of magnetic field is something we don't know so far. So that is defined by Lorentz force. So Lorentz force gives us an equation for how to calculate the total force exerted on a charge moving with velocity v, which is in the presence of electric field and the magnetic field. So there are two components to this Lorentz force. One is F electric, one is F magnetic. F electric is coming from the electric field, which is given by Q multiplied by E of R. And F magnetic is given by Q multiplied by V cross B. So now V is a vector, we know, B is a vector. So here this is a cross product of this vector. So we know from mathematics that if you have a cross product, for example, if you have a cross product A vector, cross product of B vector, then you get a final vector which is perpendicular to both the vectors, right? So V cross B has to be perpendicular to the plane where V and B are. And this is a vector. So it will give rise to a vector. So finally F is a vector. So this is called Lorentz force, which gives the total force exerted on a particle, charged particle moving with velocity v in the presence of magnetic and electric field. So we will see what are the properties of this Lorentz force. So it depends on Q, V and B. Force on a negative charge is opposite to that of the positive charge. So this is straightforward from this equation. If you reverse the direction of Q, that means if you substitute minus Q instead of plus Q, then the F becomes minus F. So if the force exerted on a positive charge is in a particular direction, let's say it's upward, then if you keep negative charge, it goes downward. So it's illustrated in this picture better. So this is a charged particle. Let's take this positively charged particle. There is a magnetic field here, and the velocity of the particle is in this direction. So there is a force exerted on this direction. So the particle deflects and it moves away from the straight path and it goes towards this way. And if you reverse the direction, if you reverse the sign of the charge, then the F actually goes just opposite direction. F is here in the positive direction, here it goes in the negative direction. And let's look at this picture also. This is charge Q. This is the velocity of the charge. That means our charge is moving this way. And there is a positive magnetic field in this direction. It makes an angle theta. So the force is in this direction, which is perpendicular to both V and B, because force is given by V cross B, magnetic force. So the magnetic force is in the perpendicular direction like this. Okay. Then what is the other property of Lorentz force? The magnetic force includes a vector product of velocity and magnetic field. Since there is a cross product, it gives a vector. So the magnetic force includes a vector product of velocity and magnetic field. The magnetic force is zero if the velocity and the magnetic field are parallel or anti-parallel. Otherwise, the direction is decided by the right hand rule or screw rule. So what do they mean by when the velocity and the magnetic field are parallel? See, there is an angle theta between V and B. What if this theta becomes 0 or 180 degree? Then V cross B gives rise to VB sine theta. Sine 0 is equal to 0. So then there is no magnetic force. So if there is a magnetic field and the particle is moving along the same direction, then it does not feel any force due to the magnetic field. So that's what this point says. The magnetic force is zero if the velocity and the magnetic field are parallel or anti-parallel. Otherwise, the direction is decided by the right hand rule or screw rule. So what does the right hand rule says? If you curl your fingers from V to B, if you curl your fingers of the right hand from V to B, then your thumb direction gives you the product direction. So here it is illustrated clearly. The curling of the fingers happen from V to B, and the thumb direction is pointing upward, which is the direction of the magnetic force. The final point is the magnetic force is zero if the charge is at rest. It's clear from this picture that if V becomes 0, V cross B becomes 0. So only a moving charge can feel the magnetic force. This is a very important point. So if that, then we go back to the static case, electrostatic case. So if you have this equation F equal to Q E plus V cross B, and if you have V equal to 0, that means the charge is just at rest, then you just get F equal to Q into E, which is the electrostatic case which we discussed before. Okay, so now we will see what happens to magnetic force on a current carrying conductor. So we talked about a single charge which is moving. A single charge which is moving gives rise to a magnetic field, and also a single charge which is moving gets affected by the magnetic field, and that force is given by Lorentz force. Now what if we have a current carrying conductor? So what is the difference here? In a current carrying conductor you have a lot of charges moving. So when you have a lot of charges moving in a steady state, what is the force that is acted upon in this conductor? By a magnetic force. That's what we are going to, by a magnetic field. That's what we are going to see in this topic. So the analysis for force due to magnetic field on a single moving charge can be extended to a straight rod carrying current. So we know about a single charge. Let's extend it to a current carrying wire. So a rod of uniform cross-sectional area A and length L has mobile carriers that are electrons. The number density of this mobile charge carriers is N. So N basically means number of electrons per unit volume. The total number of mobile charge carriers in it is NLA. LA gives you the volume. So the total number of mobile charges has to be N, that is number density multiplied by the volume. So that's straightforward. Now if you have a steady current I in the conducting rod, and you know that inside a conductor the electron moves with drift velocity, and in the presence of an external magnetic field, what happens to these electrons? That's what we are going to see. So we know that now the electrons are moving with velocity Vd. So we can start from the magnetic force equation which we learned in the previous slide. So F equal to Q multiplied by V cross B. Now Q has to be the overall charge. So now the charge carrier, number of charge carrier is NL into A multiplied by Q gives you the overall charge, and multiplied by Vt is the velocity inside the conductor, multiplied by B, this is a cross product. So this is the force the charge carriers in a current carrying wire experiences because of the presence of magnetic field. Now we can simplify this even further. This NQVD is called the current density, because you see this NQ is the charge and VD is nothing but the distance divided by time. So if you take this time element to this side, you get the current. So current multiplied by the distance, then you get the current density. So this is nothing but the current density. So NQVD is the current density J, and if you have A along with that, then you get the current. So NQVD multiplied by A will give you current. So we can replace from this equation, we can replace NQVD multiplied by A as J into A, nothing but I. So what we are left with is L cross B. So if you simplify this, then you get I L cross B. So if you look at this equation, F equal to IL cross B, it is very similar to QV cross B. Instead of Q, you have I, instead of V, you have L, and the P remains the same. So this is the force exerted because of the magnetic field on a current carrying wire, because of it has a large number of carriers. And now if you have a small current carrying element, you can calculate the force exerted by the magnetic field on this current carrying element and integrate it over all the elements, then you will get the overall force. But in this case, you have to be very careful about the direction, because it's a vector sum. So you need to worry about the direction. So at every element, you need to find the cross product and see what is the direction of that product. And you have to carefully take the vector sum. Okay. Now we will see what happens to motion in a magnetic field. So you have a charge. Again, we are going to a single charge case here. You are having a charge and you keep it in a uniform magnetic field. What happens to the charge? So when we say work done by a force, we say work done W equal to F multiplied by D. There is one important condition here. The F and D has to be in the same direction. So the force which does the work have to do the displacement in the same direction. So a force on a particle does work when the direction of the force is along the direction of motion of the particle. In the case of motion of a charged particle in the magnetic field, no work is done because the magnetic field direction is perpendicular to the velocity of the particle. So in this case, let's say the velocity of the particle is here and the magnetic field is going into the plane. That's what is represented by the cross marks here. So the velocity and the magnetic field are perpendicular to each other. So whatever work it does, the velocity is in the different direction. It's not along the force direction. So the magnetic field does not do any work. So this is an important point. The magnetic field does not do any work. It does not accelerate the particle or anything. Then what does it do? It just changes the direction of the particle. So if you look at this picture, the particle, let's say the particle is kept here, and it moves in this direction, and suddenly there is an magnetic field switched on. Then what happens? The magnetic field keeps changing the direction of the V, and it makes it rotate and makes it do a circular motion like this. So that's what a magnetic field does. So a particle with velocity V in a uniform magnetic field B perpendicular to V experiences a force Q V cross B. This is from Lorentz force, which acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. Now, okay, so that was for magnetic field alone. What if we have both magnetic field and electric field? Then what happens? So in this case, if there is an electric field, the velocity will be increasing in this direction. So we can say that the velocity has two components. One is perpendicular to the field, one is parallel to the field. Then what happens? We will see. If the velocity has a component along B, this component remains unchanged as the motion along the magnetic field will not be affected by the magnetic field. See, this is the velocity component along the magnetic field. And why it is unaffected? Because V cross B has to be 0 in this direction. So the velocity component along the magnetic field is not affected by the magnetic field. So the motion in a plane perpendicular to B is as before a circular one. So there is a perpendicular element here which gives rise to the circular motion. So the circular motion will keep happening, but there is also a velocity along the magnetic field. So along with the circular motion, the particle will keep moving towards the x-axis, positive x-axis like this. So it makes like a helical motion. It keeps moving towards the right, towards the x-axis. So now the centripetal force is given by mv square by r, which we know already. The Lorentz force due to the magnetic field when the angle between the magnetic field and B is 90 degrees QVB, because Q multiplied by V cross B. V cross B is nothing but VB sine theta. Sine 90 is 1. So we get QV into B. Now this is the force which gives rise to the centripetal force. So let's equate these two. So mv squared by r equal to qvb. So let's rearrange this equation. Let's cancel v on both sides. Then take r to the left hand side. Then you get mv by qb. So the beauty of this equation is you can decide what will be the radius of this circular motion. So you know that a charged particle moving in the presence of magnetic field makes a circular motion. You can decide the radius of the circular motion by controlling the amount of magnetic field you keep. So the magnitude of magnetic field. So it depends on what is the initial velocity of the particle, the mass of the particle, the charge of the particle, and the magnetic field. You can control two parameters here, V and T. Based on that, you can see how much will be the R. So you can decide what should be the radius of the circular motion just by controlling these parameters. Now, so the velocity is given by omega into R. Omega is the angular frequency, which is given by 2 pi nu. Nu is nothing but the frequency of oscillation. So from this, if you substitute V equal to omega into R from this equation, you get omega equal to V by R, right? So if you compare these two, then you get QB by M. So omega is given by QB by M. So the angular frequency of this particular oscillation is given by QB by M. So we know the angular frequency, we can find out the time period of oscillation. So time period of oscillation means how much time it takes for one particular oscillation to happen. So that is nothing but 2 pi by omega. So substitute omega here, then you get m by qb into 2 pi, right? Then this is nothing but 1 by nu. So it is inverse of your frequency. Now we know what is T. T is nothing but 2 pi m by qb. And what is P? P is the horizontal distance or the distance along the x-axis the particle travels in a one rotation, one particular motion, circular motion. See, for example, when the particle, let's say the particle starts from here and it goes here, it goes here, it goes here, and again it comes back to the same position, but it has made a displacement along the x-axis, this particular distance. So that distance is given by V parallel multiplied by T, because the time period of one rotation is given. So within this much amount of time, how much horizontal distance the particle has moved, that is given by the velocity of the particle along this direction multiplied by T. So P equal to V parallel multiplied by T, which is equal to 2 pi m by qb multiplied by V. So this quantity is called pitch. That is the distance moved along the magnetic field in one particular rotation, that is called pitch. So that was about motion in magnetic field. Now let's go to the topic where there are both the fields present. So there are two cases in this. One is velocity selector, one is a cyclotron. So we will see both the cases. So one is a velocity selector, and let's see, this is the picture. So there is a particle here moving with velocity v. There is an electric field pointing in the y direction. There is a magnetic field pointing in the positive z direction. So we know that if the electric field is along this direction, the electric force is also going to be along this direction. If the magnetic field is here, then according to the right hand rule or screw rule, when you calculate V cross P, then it will be pointing downward. If your thumb will be pointing downward, then you have magnetic force in the downward direction. So this is the case. And we know that the overall force is given by Q, E plus V cross P, Fe plus Fe. Now, when the electric and magnetic fields are perpendicular to each other, So we will assume a case where electric field and magnetic field are perpendicular, like in this picture. Electric field is along the y direction. So E equal to E into J cap, B equal to B into K cap because it's in the positive Z direction. And the velocity is only along the x-axis. So we can say V equal to V into I cap. Now let's substitute these quantities in this particular equation. Let's see what happens. So the Fe becomes QE into J cap. FB becomes Q V cross B. V is nothing but V I cap multiplied by B K cap. So if you take I cross K, it is minus J, and you can take QVB outside. Then what you get is minus QBJ. Now what happens? Okay. So you can find out the overall force. So this is minus QVBJ. So you take the overall force equal to Q multiplied by E minus VB into J. So this is the overall force that is acting on the particle. Now, what if this force is 0? What if the net force is 0? Let's assume a special condition when the net force is 0. If the net force is 0, then the particle that is moving along the x-axis will go without any disturbance. So in other words, it will go undeflected, right? So what is the condition for this net force to be 0? It is QE equal to QV into B. So if you equate F equal to 0, then it means QE equal to QVB. So the magnitude of B and E are adjusted in such a way that the magnitude of the forces Fe and Fb are equal and opposite because of the sign. So the net force on the charge is 0. This is true only when the condition is satisfied. So what does this condition tell us about the velocity of the particle? So the velocity of the particle, if you rearrange this, has to be in such a way that it is the ratio between the electric and magnetic field magnitudes. So V equal to E by B. So in this kind of a configuration, only the particles which have the velocity of E by B will be undeflected, will go undeflected. So by assuming this condition, we can select the particles with a particular velocity to go to come out of this particular situation unaffected by the fields. So for example, if you have a bunch of particles with different velocities, but you want the particles with only particular velocity to come out undeflected, for some experiment you want to use this. So how can you do that? You can design an experiment with this. So you can keep your electric field and magnetic field in such a way that only this particular velocity comes out. So that is why we call this a velocity selector. So this is an application of using electric and magnetic fields in the same particle. Okay, so the next case is a cyclotron. So cyclotron is a machine to accelerate charged particles or ions to high energies. So in the previous case, we did not accelerate the particles. The velocity of the particle did not change. But in this case, we are going to accelerate the particle by using both electric and magnetic fields. So this is useful in many experiments. For large hadron colliders, when you want high energy particle in synchrotron, in nuclear reactors, when you want high energy particle to come out, then you can do that by using this particular cyclotron. So you can accelerate the charged particles. So the structure of the cyclotron is in such a way that it has two D-shaped metal containers. So we will see that the cyclotron uses both electric and magnetic fields in combination to increase the energy of charged particles. The fields are perpendicular to each other and they are called crossed fields. Because they are perpendicular, we call them crossed fields. Cyclotron uses the fact that the frequency of revolution of the charged particle in a magnetic field is independent of its energy. In a cyclotron, the particles move most of the time inside two semicircular disc-like metal containers D1 and D2. Inside metal boxes, the particle is shielded and not acted on by the electric field, but feels only the magnetic field. So this we already know that inside a metal, the electric field cannot penetrate, right? We talked about this in the case of electrostatic shielding. So we have two D-shaped metal containers. When the particle is traveling inside this container, it does not see the electric field, it only sees the magnetic field. So when the particle just sees the magnetic field, what happens? The path only becomes circular, right? The velocity does not change, but the path only becomes circular. So this is the situation. Let's see what happens then. every time the particle goes from one D to another, it is acted upon by the electric field. The sign of the electric field is changed alternatively in tune with the circular motion of the particle. So let's say the particle starts from the center, and the right hand side D has a positive or a negative potential depending on the charge of the particle. Let's say that it attracts the particle or accelerates the particle towards the right hand side. When it comes inside this metal, then the electric field is not affecting the particle anymore. So it makes a circular motion because of the magnetic field. Then it comes out of the D. Then again it gets accelerated because of the potential of the left hand D. Then again it goes here, again it makes a circular motion, it goes here, again it makes a circular motion. Like this it keeps continuing, and you see in every circle the radius of the circle keeps increasing because every time it gets accelerated. When it gets accelerated, the velocity increases. When the velocity increases, the radius also increases. And finally, when the radius of the circular motion becomes equal to the radius of the D, then it comes out. So there is an exit port here where the particle comes out. And the particle here which comes out has much higher kinetic energy compared to the particle which started at the center because it gets accelerated in every rotation. So we will see this in detail. This makes sure that the particle is always accelerated by the electric field. So whenever the particle experiences the electric field, it gets accelerated. And every time the particle accelerates, its kinetic energy also increases. As the energy increases, the radius of the circular path also increases. High frequency alternate voltage is applied to the Ds. And now we know already that omega equal to 2 pi by D equal to QB by M. We derived this equation in the previous slides. And now the time period also we know, which is given by QB by 2 pi M. Now the frequency, if we calculate from this, it is 2 pi M by QB. This is called cyclotron frequency. So this is the frequency of oscillation of the particle inside this cyclotron. So this is controlled by the magnetic field magnitude and the charge and the mass of the particle. Now this is the cyclotron frequency. Now the frequency which we are giving to the Ds, that is, we are giving an alternate potential to the semicircles here, and the frequency of this applied voltage has to match the cyclotron frequency. So the frequency VA of the applied voltage is adjusted so that the polarity of the Ds is reversed in the same time that it takes the ions to complete one half of the revolution. So the requirement VA equal to VC is called the resonance condition. So for example, when the particle is here, let's say it gets attracted to this, and by the time it makes a half rotation and comes here, the polarity has to change in such a way that the particle again gets attracted towards this. So that is why the alternating potentials frequency has to match the cyclotron frequency. So the radius of the path of the particle keeps increasing every time their kinetic energy increases. The ions are repeatedly accelerated across the Ds until they have the required energy to have a radius approximately that of the Ds. Once they have the radius, they are deflected by this magnetic field and leave the system via an exit slit. The velocity of the particle leaving the D is where R is the radius of the D. So the velocity is decided by this R. Let's see how it works. So we know that centripetal acceleration or centripetal force is given by mv squared by R equal to QVB. Now from this we already derived R equal to mv by QB. And from this we know V equal to QB by QBR by M. So if this is the V, then what is the kinetic energy? Kinetic energy of the particle is given by half mv squared. So substitute V here, then we get Q squared B squared R squared by 2M. So this is the kinetic energy. So this is dependent on your R. So it means that how much ever big is your D, that much kinetic energy you can get. And also you can control this by varying the magnetic field and by varying the charge of the particle. In most cases, the only parameters which we can vary is the magnetic field here. So this is how we can accelerate a charged particle inside a cyclotron. So in the previous cases, we talked about how much the current carrying wire is affected by the magnetic field. But in this case, we are going to talk about magnetic field produced due to a current element. And this law is given by Biot-Savart law. So this is similar to Coulomb's law because Coulomb's law gives us what is the electric field produced by a current electric charge. In this case, this law is going to give us what will be the magnetic field produced by a current element. So the relation between current and the magnetic field produces is given by the Biot-Savart law. So consider an infinitesimal element dl of the current carrying conductor xy carrying current I. The magnetic field dB due to this element is to be determined at a point P which is at a distance r from it. So this is the current carrying element xy where I current is flowing. Let's take a small element called dl, and this is IDL is the current flowing through this, and we will take a point P at a distance r from the element, and we are going to find out what is the field produced at this particular point, that is dB, due to the current element. So whenever there is a current, it gives rise to a magnetic field, we know. So in this case, we are going to take a current carrying element and see what is the magnetic field produced by this particular element. According to Biot-Savart law, the magnitude of the magnetic field dB is proportional to the current I, the element length dl, and inversely proportional to the square of the distance r. So similar to Coulomb's law, this also follows an inverse square law. Its direction is proportional to perpendicular to the plane containing dl and r. This comes from the right hand rule, which we already discussed. So let's see what is the magnetic field depends on. The magnetic field is proportional to IDL multiplied by r divided by r cube. So now we have, why we have r cube here instead of r squared is because here we have r instead of r cab. So that's why we have an r cube here. Otherwise it's supposed to be r cab, that is the unit vector. So if you simplify this, or you introduce a proportionality constant mu 0 by 4 pi multiplied by IDL cross r divided by r cube. So this is what Biot-Savart law gives us. It gives us what is the magnetic field produced by a current carrying element dl. And now the magnitude of this is from the direction, and if you take the magnitude of this, dl cross r can be written as IDL sine theta, and r is nothing but r multiplied by r cab. So if you ignore r cab and just take the magnitude, then r and r cube becomes r square here. So that's why you have dB equal to mu 0 by 4 pi IDL sine theta divided by r square. So that's how it gets the inverse square dependence, just like Coulomb's law. So now mu 0 by 4 pi is called the permeability of free space, and it is given by 10 power minus 7. So this is the proportionality constant, and it's similar to epsilon 0 which we talked about in Coulomb's law, which is called permittivity of free space. Okay, so we can compare the Biot-Savart law of magnetic field to the Coulomb's law for the electric field. So both are long range and follow inverse square dependence on distance. Principle of superposition applies to both the fields. So this is one similarity between both the things. And the electrostatic field is produced by a scalar source, the electric charge, because charge is a scalar quantity. But the magnetic field is produced by a vector source called IDL. That is, IDL is a vector. So unlike electric field which is produced by a scalar, magnetic field is produced by a vector. So another important difference between electrostatic field and the magnetic field is the direction. So generally the electrostatic field is along the displacement vector joining the source and the field point. But the magnetic field is perpendicular to the plane containing the displacement vector and the current element. So if you consider a current element here and r here, so this blue arrow represents the current element, r represents the distance vector, the magnetic field will be perpendicular to the plane containing these two vectors because it's a vector product. Okay. So there is an angle dependence in the Biot-Savart law which is not present in the electrostatic case. In electrostatic case, there is no angular dependence because it is not a vector product or anything. But in this case, it's a vector product. So the magnetic field at any point in the direction of dl is 0 because we know that if the magnetic field is along this direction, then theta is going to be 0, right? So sine theta equal to 0, then dB becomes 0. There is an interesting relation between epsilon 0, the permittivity of the free space, and mu 0, the permeability of free space, and it's connected through the speed of light. So This is what connects electricity and magnetism and gives rise to the electromagnetic theory, where the permittivity and permeability decide the speed of light in vacuum. So the product of epsilon 0 and mu 0, if you calculate, it gives you 4 pi epsilon 0 and mu 0 by 4 pi, because we know the values of these two quantities. So you have 1 by 9 multiplied by 10 power 9. Mu by 4 pi, 4 pi is given by 10 power minus 7. If you simplify this, then it gives rise to 1 by 3 multiplied by 10 power 8 the whole square, which is nothing but 1 by c square. So the product of epsilon 0 and mu 0 gives the gives 1 by c square, where c is the speed of light in vacuum. Okay, so now we are going to talk about magnetic field on the axis of a circular current loop. So in the previous case, we just had a piece of current carrying conductor XY, and we took a small element and we calculated what is the magnetic field due to that small element. Now it's the time to integrate it. I mean, we have a circular conductor, and we have a circular conductor like this, where current is flowing in, steady current is flowing. Now we want to find out what is the magnetic field at a point P, which is along the axis of the circular loop. So if this is the axis that is going through the center of the loop, and along this axis at a distance x from the center, we want to find out what is the magnetic field. So R is the radius of this loop, and there is a current flowing, and the loop is kept in YZ plane. So this is x plane, x direction. So we want to find out the x-axis is the axis of the loop. So we want to find out what is the magnetic field along the x-axis. So calculate the magnetic field at the point P on this axis. Let Z be the distance of P from the center O of the loop. So now consider a conducting element dl of the loop. So we will just take a small loop and find out what is the magnetic field given by this loop, and then we will integrate it over the circular loop. So first let's start a small element dl. Let's take a small element dl and find out what is the magnetic field due to this dl. So from the Biot-Savart law, we know dB equal to mu 0 by 4 pi I dl cross r divided by r cube. Now r square from the Pythagoras theorem, see this triangle is a right angle triangle. So you have r square equal to x square plus r squared, and we know dB given by the Biot-Savart law. Let's see how to calculate the overall B. So any element on the loop is perpendicular to the displacement vector from the element to the axial point. If you take this loop, small element, it goes in this direction, and the R is in this direction. So R is perpendicular to this DL here. So they make 90-degree angle, and we have DL cross R. So if you have 90-degree angle, it gives rise to R DL sine theta, and sine 90 is 1. So we can replace DL cross R as R DL. So dB equal to mu 0 by 4 pi I DL cross R becomes dB equal to mu 0 by 4 pi I r dl divided by r cube, and r we can cancel out, and so we get r square here, and we know what is r squared from the Pythagoras theorem. It is x squared plus r squared. So finally we get mu 0 by 4 pi I dl divided by x squared plus r squared. So the direction of this dB is given by this. So it has two components, one component along the x-axis, one component perpendicular to the x-axis, right? So when you move along this loop, when you take small elements along this loop, the perpendicular component keeps rotating in this plane, so it eventually gets cancelled. So for every element here, there will be another element here which will produce another component here in the opposite direction. So the perpendicular components gets cancelled when you integrate along this loop. So there are two components for dB. It has an x component dBx and a component perpendicular to x-axis called dB perpendicular. The components perpendicular to the x-axis get cancelled when summed over. So the only surviving component is the x component. So the net contribution along x component can be obtained by integrating dBx equal to dB cos theta over the loop. So why is it dB cos theta? Because dB makes an angle theta along the x-axis. So this projection is going to be dBx cos theta. So dB cos theta you have to integrate along the loop. So we have cos theta. Cos theta can be calculated from this right angle triangle, Again, this angle here is 90 minus theta. If you look at this particular line, you can know that this angle is 90 minus theta. So sine of 90 minus theta equal to r divided by small r, which is nothing but cos theta, right? So cos theta can be written as r divided by x squared plus r squared the whole power 1 by 2. And now let's substitute this particular value of cos theta into this equation. dbx equal to db. Instead of db, we have mu 0 by 4 pi idl divided by x squared plus r squared multiplied by cos theta. Instead of cos theta, we have this quantity. So we get finally mu 0 idl divided by 4 pi r divided by x squared plus r squared the whole power 3 by 2. So this is the x component of field produced by this one small element of length dl. So if you want to find out what is the x component, summation of the x component of the whole loop, then we have to replace this dl by the circumference of the loop, which is nothing but 2 pi r. So the summation of elements dl over the loop yields 2 pi r, the circumference of the loop. So the magnetic field at P due to the entire circular loop is given by B equal to Bx I cap. I cap represents x direction. So you get, if you substitute 2 pi r instead of dl, then you get mu 0 I r squared divided by 2 multiplied by x squared plus r squared the whole power 3 by 2 into I cap. So this is nothing but the field produced by a current carrying wire, circular wire, at a distance x from the axis, from the center of the axis, right? So now to calculate the special case, what if we move this point to the center? So when we move this point to the center of the loop, then x becomes 0. So if you substitute x equal to 0 here, then you cancel out r squared and r squared, then you finally get b0 equal to mu 0 I divided by 2r into I cap. So this is the magnetic field at the center of the current carrying loop. For example, if you think of this as a current carrying loop, at the center of this loop, this is the value of the magnetic field. So the magnetic field lines due to a circular wire form closed loops as shown in the figure. So this is a circular wire. The magnetic field lines form a circular loop. So this is again much different compared to the electric field, because electric field never forms a circular loop, because electric field always starts from positive charge, it ends at negative charge. This is a very important point, because magnetic field always has loops, because magnetic monopole do not exist. There is no magnetic monopole. Magnet always has a dipole. For example, if you have a bar magnet, if you keep cutting the bar magnet to smaller bar magnets, then every time you cut the bar magnet, you get again north and south pole. You cannot separate north and south pole of a magnet. That is why we don't have magnetic field originating from a pole ending at another pole, unlike electric field starting from point positive charge and ending at negative charge. So this direction of this magnetic field is given by the right hand thumb rule. So for example, if this is the current carrying loop, you curl your fingers of your right hand as your current carrying loop, and the thumb direction will give you the direction of the magnetic field. So curl the palm of your right hand around the circular wire with the fingers pointing in the direction of the current. The right hand thumb gives the direction of the magnetic field. So this is about the magnetic field produced by a circular current loop. So first we took a small element and we calculated overall magnetic field. Then we also discussed about the direction of the magnetic field produced by a circular current loop. Thank you.
Why waste time in commute and spend a lot of money for IIT JEE coaching? Parents, do you want your kids to achieve top scores in IIT JEE? India's leading online NEET coaching 100% success IIT JEE. At TeenEinstein, we focus on IIT JEE coaching from Class 6 to Class 12. We think you'll like it. Our teachers are mostly PhDs in physics, maths, chemistry, botany, and zoology, with lots of years of teaching experience for Class 6 to Class 12. Thousands of videos, quiz, MCQs. We provide a daily worksheet of 30 questions on each topic: math, physics, chemistry, and biology, for rigorous practice, concept understanding, evaluation, quiz, and thousands of videos. Limited offer 40,000 rupees per year. Book your class. TeenEinstein.com.